So good morning. In the last lecture, I looked at a fascinating example. At least it fascinated me, and explored it over a duration stretching to some 2.5 hours. It's still towards the end I had to rush through certain ideas, and since this is a series of lectures for the students, I thought that maybe I'll do some more of it to give them some insight into how actually one goes about analyzing a problem. In fact, nothing is barred while doing mathematics. I mean, everything legitimate, of course. Yeah. At least at the exploration stage, you can do whatever you like. And eventually, the mathematics has to be expressed in the right kind of language. I mean, that's the only thing that you have to be careful about. But let me come back to this example. So, the example was this. You have two functions, uxy defined as x square plus y square, vxy defined as 2xy, then phi is a map from R2 to R2, and this is defined xy getting mapped to uv in R2. So these are the notations. Now you see that phi is C1 That's quite easy to see because you are working with a very smooth polynomials. In fact, it is much more smooth than C1. Now, you see that we look at the places where phi derivative is singular. Okay, so you see that phi derivative this is a linear transformation, and you are taking the see, this belongs to L R2. This is singular for, if you work out the determinant of this with respect to the standard basis, it will become x square minus y square, and x square minus y square equal to 0 becomes singular. Okay. So that is along x equal to that means along these lines, this is x equal to plus y and this is x equal to minus y. This is singular. Elsewhere, phi dash is inverted. Okay. So if your xy is somewhere here other than these lines, phi dash is invertible. Now let us look at the range of this. I mean, this we have very extensively explored. Domain is, of course, is R2, xy plane, and domain, the range of phi this is equal to set of all such that u is greater than or equal to 0, V is such that mod V is less than. That means this wedge-shaped region which we designate by V. Then of course therefore phi is a map from onto. Now we observe that the regions that I have marked as W1, W2, W3, W4, okay. So W1 we have W2 equal to xy, where y is positive and mod x is less than or equal to y. W3 is x is negative and you have mod y and W4 y is negative and mod x so these are the four regions that we identify. Then we observe that phi is a map from Wi onto and phi is 1 to 1. This is what we have proved. So this is true for I, which means each of these wedge-shaped regions get mapped to V and the mapping is 1 to 1 and on. And you see that the interior of Wi is an open set and for every xy belonging to interior of Wi, what one has is that phi dash xy is here. So everywhere here in the interior, the phi dash is invertible. Therefore, now the inverse function theorem is applicable to phi. What do we conclude? Okay. The inverse function for every x, y belonging to interior of Wi, there exists an open set U, capital U, there exists open sets U containing xy and V W or I will use V, using V for something else also, therefore let me write xy script V. Such that on to V comma 1 to 1. So this means, of course, V equal to one to one. Such a U and V exists. Okay, and then of course what we expect is that phi, if G is from V to U such that phi of G of that is the inverse map, or G is the inverse map, then G is C1. from further G of G prime inverse where now this we have in fact verified. Okay, but I have come back again to discuss this problem only to indicate certain interesting information. Therefore, what do you have in our problem? In our problem, what happens? So let us write down what they are. I say I equal to 1 or these are the 4 options. Now let us work it out. It's interesting to see what turns out. Let the interior of okay. When you observe that phi is a map from Wi to V. More especially, also from interior of, okay, I will write it as interior of interior. Both are open and they are, this is AB, that is interior of Wi is an open neighborhood of AB. So choose this as now V is the map phi from interior of Wi to interior of is 1 to 1 on hence phi u equal to ATO. Okay. So what more you get? Now what the theorem says is the following. Okay, hence phi is invertible. That is, there exists a map G from U, that is from interior of V to interior of Wi, such that belonging to U. Therefore, we are taking U as the interior of Wi and V as the script V as the interior of the wedge V that we have chosen. Okay, clear. And both F and phi and G are the inverse operators and they are 1 to 1 and on to. Now this is what we have proved. So the first statement of the theorem holds. That means given AB where phi of AB is, that is then phi of invertible. So only when you are on these lines x equal to y and x equal to minus y, phi is not invertible. So on every point in the interior of Wi for I equal to 1 to 4, phi is invertible. Okay. Moreover, we have verified that we have explicitly G from V to Wi. Now we have explicitly written it on from V to W1, V to W2, V to W3, V to W4. These four maps we have explicitly written in the last lecture. Further, G is C1 on V and we also have g derivative at inverse for every belonging to Wi interior of Wi, okay, which we have taken as u. This variable. And uv u this is what you have, okay, and this we have verified every bit of this, right? Now what more we need? Make certain observations, because in proving this, how one can make use of the polar coordinates. I have indicated how you can do this using okay. So we take x equal to r cos theta, y equal to r sin theta. Then r is, of course, r is greater than or equal to 0 and theta lies between less than, takes care of the entire set of points in R2. Now what is that you get from here? Then you observe that u r square equal to r square cos 2 theta, not cos 2 theta, sin theta. Therefore, the image of r cos theta, r sin theta is r square sin 2 theta. So you have is this phi maps Now this is your V. Now you clearly see that, see, this gives u equal to r square V equal to R square sine 2 theta. Okay. Now you see that the image of x equal, so from here it follows that x is, or that means the range of the set of all UV with R square and so this is our, so that is easy to see here, doesn't go out of that. Okay. Also observe that every radial line which is corresponding to theta equal to constant gets to in particular what happens, the radial lines x equal to plus or minus y for yeah, and x equal to y get mapped to u equal to and x equal to minus y mapped onto u equal to minus. That is quite easy to verify. the line, the radial lines y equal to 0 and x equal to 0 the radial line is it. That means what I mean to say is this gets, see, this portion as well as this portion, they get mapped to this, and this part as well as this part get mapped to this portion. Further, this whole line and this whole line gets mapped to the radial line v equal to 0. That's a very interesting piece of information. In addition to that, you take any radial line that you get mapped. Okay? And an arbitrary point on that is going to be r square comma r square sine 2 theta. So if this angle is theta, then sine 2 theta fixes up the particular line. It is not the angle is, it's not of the form, say r square cos 2 theta and r square sine 2 theta. It is of the form r square comma r square sine 2 theta. Okay, so that's the map that you have. So in fact, we have finer information about this map. This is the important thing. We know exactly how these maps take place. And on all these radial lines, see the corresponding radial lines in the domain space, the map to the corresponding radial line on in V is 1 to 1 and 1 to 1. So that's an important information. Okay. Now, how do we find out the image of a point in V in the xy plane? So, how to? The pre-image, I will put it this way. So here you can see, that means you want to find out the pre-image of a point in this plane, in the UV plane over here. See, for each point, in the xy plane, one each in it's 3 each. This is the important thing. So how do you fix this? Okay, so let us work it out. Start with, so belonging to V. Is positive. Therefore, set R1 equal to square root of positive square root of U1. Now we have to fix theta. V1 can be written as U1 sine theta 1, sine 2 theta 1. Okay, then what happens? The pre-image square root of U1 cos theta 1 that is what it comes. So you see, you have now, you can see that there are 4 possible choice that you can make for the theta 1. There are possible choices that one can make. Each theta 1. Okay. Now let us explore this. How do we explore this? We explore it as follows. Let us take zero. Okay. then what are the possible choice that you can make? So look at the diagram here. See, you have the graph of sine 2 theta drawn from here from minus pi by 4 all the way up to 7 pi by 4. Okay, it has got two maxima and possibly this is a minima and the endpoints are all minima. Okay, so it takes the value plus 1 and minus 1 when let's see, theta takes the value minus pi by 4 and pi by 4 respectively. Okay, now let us fix the sine 2 psi. Sine 2 psi, because psi is taken to be non-negative and we have 0 less than or equal to psi less than or equal to pi by 4. If so, what are the values for which you will get the same value for u1 and v1? Now you see that from here it is quite clear. So this is psi. The next value for which sine 2 psi takes the same value is pi by 2 minus psi. So for psi, pi by 2 minus psi, then what are the values? Pi plus psi and you have 3 pi by 2 you have equal to sine 2 psi. Takes the same value. Okay, therefore see the corresponding value root u cos theta gets mapped to what is called u, then u sine 2 theta which is equal to u sine 2 psi for theta equal to psi, theta equal to pi plus pi by 2 minus psi, theta equal to 3 theta equal to what is the third value? The third value is pi plus psi equal to 3 pi by 2. Now you see that each of these value choice of psi corresponds to the point in W1, choice of pi by 2 minus psi corresponds to a point in W2, choice of pi plus psi corresponds to a point in W3, and the choice of 3 pi by 2 plus psi is a point in W4. Now these are the 4 points, one each in each of these regions, which get mapped to the fixed UV that you want to choose. Okay, so there is some xy here, and then the next choice is that pi by 2 minus psi is somewhere here. So you have the corresponding xy. How do you get the next one? The next one corresponds to this one. This is y x. This is y x. That is the relation between these two. Okay. Then what about this theta equal to pi plus psi? Theta equal to pi plus psi corresponds to the mapping from xy to minus y. And then theta equal to 3 pi by 2 plus psi corresponds to this point. So you have got this as a reference. Okay. So x, y, so this is equal to minus y minus x. You can easily check that they all get mapped to the same point UV. This is, I am choosing V to be positive. That means I am choosing the corresponding theta or the psi I have chosen positive and lies somewhere here. So this is your psi, and this portion is what is it? Pi by 2 minus psi. Okay. Then this one, this angle is what? Pi plus psi. And what about this angle? This particular angle that you have corresponds to 3 pi by 2 So every point here has correspondingly 4 points in this plane, and that has been identified using this picture. Now likewise, you take theta equal to minus phi, where phi is positive but it's negative, so that it lies between minus pi by 4 and 0. That means you will be choosing a point here, and then the corresponding values you can get, and those values you can get from here, because you see that you have minus phi, and then this is related, this is pi by 2 plus phi, which gets mapped to this. Phi is positive, of course minus phi is negative. Then pi minus phi, sine 2 pi minus phi, sine 2 pi by 2 plus phi, sine minus phi minus 2 phi, and sine 2 3 pi by 2 plus phi. They all have the same value, so they all get mapped to the corresponding point here. So you can mark those points in this figure. So you will get 4 points now. Those 4 points will be something here and then something here, okay, and then something here, okay, and then what you get, because you see that yeah, not here, something here, what did I say? See, I have a, yeah, start with a 5 here, then what is the other point that I have? -5, then you have pi by 2 plus 5, okay, pi by 2 plus 5 is, you are here, and then you are inverting, okay, and then happen. So you get the points in W2 and W4, okay, sorry, not here, W2 and I'm not saying, I'm saying that there is a point in W1, there is a point in W2, there is a point in W3, and there is a point in W4. They all can be obtained. You can write down like this. Okay, so I'll write down those points. So with polar coordinates, you can actually see what exactly is going on. So the why I have been repeating this using polar coordinates is to show that there are various ways in which you can work out these ideas. Okay. So one observes the following. Okay, so for you choose theta equal to -1, where okay, then UV, the corresponding UV equal to, what do you have? It is U and yeah, U cos minus U sin 2 phi. U is equal to R square. So what do you get as R? So the image points are the pre-image points where R equal to square root of U and theta equal to -5, theta equal to, what are the other values that you have? Theta equal to -5, theta equal to pi by 2 plus 5, theta equal to pi minus phi and theta equal to 3 pi by 2 plus 1. It comes like this. You fix this one. Once you fix this thing, you search for the corresponding value of phi. So you get minus phi here. Designate this point as minus phi. Therefore, phi is taken as positive and lying between 0 and pi by 4. So that minus phi lies between minus pi by 4 and 0. And for that, you write down everything. So this is going to be pi by 2 plus phi, where it takes the same value. Then at pi minus phi, it takes the same value. And 3 by 2 plus phi, it takes the same value. Okay. The v value remains the same. Or sine 2 theta takes the same value. Okay. So these are the 4 values. And this corresponds, the first one corresponds to, so these are or I'll write this way, the corresponding points belong to W1, W2, W3 and S1. So that's how you get this, and it's quite easy to, I have shown last time how to prove that these maps are one-to-one. Therefore, what do you get? So your U is now chosen as interior of W1. V is now chosen as interior of V. And you see that your maps are phi, and 2 inverted. And if G is the inverse map, or if you want, you can even write it Gi is the inverse map. It is Gi from V to Wi. What you have is that the following is phi of G prime of UV is equal to this, where U comma V belongs to interior of V and now this is the complete analysis of this map. Okay, and I have already given what are the inverse functions, and you will have to use the inverse functions to calculate this. I have computed in one case that the relation connecting these two, that is taking W1 and V. I have computed this. Okay, or at least one, what you call a, in fact it is much more interesting. See, the upper portion of V gets mapped to the upper portion of W1, and probably there is a corresponding part in W2, W3 and W4, and this particular wedge goes to the other half of this, and there is a corresponding thing. Okay, I want to make one more remark. See, there is a map from, see, how do you get these maps, the corresponding points? If xy corresponds to uv, then yx corresponds to uv minus, okay, so let me just write down that also, going back to the Cartesian frame, how they are related. It's interesting to see how these things come out. Okay, so you observe the following. Okay, this is the picture. This is your V. Now you see that you have W1, W2, W3, W4. Okay. So you start with a UV. Then you have a corresponding X1, Y1. So that this Y. Now how do you get, what are the other points that get mapped to it? You will get Y1, X1 also get mapped to this. What is Y1, X1? Y1, X1 is this point. Y1, X1 is in W2. Okay. Now you take X1, Y1 and go take inversion. Okay. Or reflect it about the origin, and what do you get? This is minus x1 minus y, and again reflect it. This is equal to minus y1 minus x. Okay, so you see that once you are in W1, from W1 to W2 there is a 1-to-1 map. What is that 1-to-1 map? The 1-to-1 map is reflection about this line. It is reflection about the line I have marked. So this is the reflection map. So you have the corresponding uniquely determined point. Okay, so this reflection about the xy plane is a one-to-one map from where to where? Okay, you take W1, consider y1 x1 and x1 y1 belongs to W1 implies y1 x1 belongs to W2. Then you have minus x1 minus y1 belongs to W3 and minus y1 minus x1 belongs to W. This is the connection. So these are the same point. I mean these points are the one which gets mapped to UV. They all now, if on the other hand, suppose you start with something, some xy here, or suppose this is the then what happens? This also gets mapped here. See, this also gets mapped there. This also gets mapped to this point. Likewise, what you have is this x2, y2. This x2, y2 gets mapped to this one. And then you have the corresponding image points. What are the image points that you have? One image point is to take its reflection here. You see, this is in W1. Okay. Now, so this is in W3, and this is in W2, and this is in W4. Okay. So you can use these reflections. That is, these reflections are reflection about x equal to y or x equal to minus y are one-to-one onto maps. Likewise, the reflection about the point or about the origin is also a one-to-one onto map. So use that invertibility of these two maps and then combine this as the composition of these maps would give you the corresponding image. So one can use this reflection. That's the beauty. So you can use that to prove all these things, and I think there are various ways in which you look at this problem. Now, the why I unnecessarily harped on this for sufficiently long is just to show you that even at the time I started analyzing this, started with the problem, I just wanted to give an example where I can work out the inverse function theorem on a given function. That's why I started. I didn't expect this much to come out of this. But when I started analyzing, it found that it's a wealth of excellent mathematics that comes out of it. And there are various ways of investigating it. And I have given a glimpse of this. There may be many more things that you can read out. See, there are a lot of things like the radial lines get mapped to the radial lines, etc., etc. All this, the complete lot of information about this map is now available on this. Okay, with these remarks, I conclude this. So, thank you very much.